The line of sight. Welcome, everyone. Today, we are beginning a new topic titled, the line of sight. Now, as you move further into your study of trigonometry, specifically when we start tackling more complex problems involving heights and distances, you'll notice that we aren't just working with abstract numbers. Instead, we are often faced with real-world physical scenarios, like measuring the height of a tower or the distance of a ship at sea. To solve these, our first and most important task is to translate those real-world scenes into accurate mathematical diagrams. To do this successfully, we need to master the most fundamental element of these diagrams, which is known as the line of sight. We will define exactly what this means and how to use it in the following slides. Understanding the concept. Now that we've introduced the importance of translating real-world scenarios into diagrams, let's dive deeper into what the line of sight actually is. By definition, the line of sight is an imaginary straight line that we draw from the eye of an observer directly to the specific point on the object they are looking at. To make this concept much clearer, let's break it down into three simple components. First, we have the observer. I want you to imagine a person standing at a specific location. When we are performing these mathematical measurements, our starting point is always the observer's eye, not their feet. Second, we have the object. This is the target of our gaze. It could be anything, like a tall tower, a bird in the sky, or a large building. And finally, we have the connection. Think about the path that light takes as it travels from that object back to your eye. Because light travels in a perfectly straight path, we represent this connection in our geometric diagrams as a straight line segment. As we will see in the next slide, this connection is the key to setting up our mathematical coordinates. Real-world example. Now that we have established the theoretical definition of the line of sight, let's move from the abstract concept to a concrete, real-world example to see how we actually apply this in a diagram. Imagine for a moment that you are standing in a park and you look up into the sky to watch a kite flying high above you. This is a perfect scenario to practice our mathematical modeling. To translate this physical scene into a geometric diagram, which is exactly what we will need to do for the more complex trigonometry problems we'll see later, we follow three simple steps. First, we need to identify our starting point. We will represent the position of your eye as point P. Second, we identify the object we are observing. In this case, we will represent the position of the kite as point K. Finally, we connect the two. The straight line segment connecting point P to point K, which we denote as PK, represents your line of sight. As you can see, by assigning these points, we have turned a simple moment in a park into a measurable line segment that we can use in our calculations. Geometric significance. Now that we understand what the line of sight is, let's look at why it is so important when we actually start solving math problems. In most height and distance problems, our ultimate goal is to create a right-angled triangle. Why? Because once we have a right-angled triangle, we can use our trigonometric ratios, like sine, cosine, and tangent, to find unknown values. The line of sight plays a critical role in constructing this triangle. Think about a typical scenario. You are standing on the ground, looking up at the top of a tall building. In this setup, the height of the building acts as our perpendicular or the opposite side. The distance along the ground from you to the building acts as our base, which we call the adjacent side. Because the line of sight is that straight, diagonal path we discussed in the previous slides, it naturally becomes the hypotenuse of our right-angled triangle. To make this even clearer, let's look at a specific example. Suppose we have an observer located at point A, looking up at the top of a tower, which we will call point B. The foot of the tower, where it meets the ground, is point C. If we map this out, the distance from point A to point C is our base. The height of the tower from point C up to point B is our perpendicular. And finally, that line of sight, the straight line connecting point A to point B, which we denote as a B, serves as our hypotenuse. As we move to the next slide, we will summarize the key points we've learned so far. Key takeaways. First, remember that the line of sight isn't something you can physically touch. It is an imaginary line that connects the observer's eye directly to the object being viewed. Second, because light travels in a direct path, we always represent this line as a straight line in our geometric diagrams. Finally, this is a crucial point for your upcoming trigonometry problems. When we are constructing right-angled triangles to solve for heights and distances, the line of sight usually serves as the hypotenuse of that triangle. All right, let's wrap up what we've learned today by reviewing the key takeaways. Now, before we finish, I want to highlight a few common pitfalls that students often encounter when they start solving these types of problems. Common mistakes to avoid. First, watch out for confusing the line of sight with the horizontal level. When you are looking at a diagram, a common mistake for beginners is to mistake the ground, which represents the horizontal distance or the base of our triangle, for the line of sight itself. Always remember what we discussed in the previous slides. The line of sight is that diagonal path your eyes take to see the object, not the flat path you would walk on the ground. Second, be careful not to ignore the observer's height. As we move into more advanced problems, you'll notice that the observer's eye level isn't always resting directly on the ground. For instance, a problem might state that the observer's eye is 1.5 meters above the ground. In these cases, you must remember that your line of sight starts from the eye level, 1.5 meters up, rather than from the base of the observer's feet. Always ensure that your line of sight originates precisely from the eye to ensure your geometric construction is accurate. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even when you understand the definition of the line of sight, it is very easy to make certain errors when you start solving complex trigonometry problems. If you keep these 2 points in mind, you will be well on your way to mastering heights and distances.